Last time, we briefly explored the reasons why Moore's law had to be broken. Today, let's dive deeper into the phenomena caused by physical limitations. First, there's the phenomenon known as crosstalk. This occurs when the EM fields created by accelerating electrons generate opposing forces, causing data to become corrupted. Apart from crosstalk, there are several other physical factors that contribute to the limitations of Moore's law. Quantum tunneling is another critical factor. As transistors become extremely small, electrons can pass through physical barriers via the tunneling effect. This makes it difficult to clearly define the on-off states of transistors, leading to malfunction. There are also limits to semiconductor materials. Traditional silicon-based semiconductor materials face challenges when reduced to very small sizes, as electron mobility decreases and electrical characteristics may change. Lastly, there's the issue of heat dissipation. As more transistors are packed into smaller spaces, it becomes increasingly difficult to effectively dissipate the generated heat. Overheating is a major factor that shortens the lifespan of chips and degrades performance. Researchers are exploring various approaches to overcome these physical limitations. First, they are searching for new materials. Researchers are investigating new semiconductor materials like graphene and carbon nanotubes, which may overcome the limitations of traditional silicon. They're also exploring 3D integration technology, which addresses density issues by stacking chips vertically rather than expanding them horizontally. Another approach involves using optical signals. Optical computing, which uses light signals instead of electrical signals, is gaining attention as a way to reduce signal interference. Unlike electrons, photons do not interfere with each other. If controlling the speed of electrons isn't possible, a complete shift in the underlying mechanism might be necessary, such as quantum computing. Quantum computers use qubits instead of traditional bits, potentially revolutionizing computational performance. Let's take a closer look at each of these. First, let's talk about graphene. Graphene is a single atom-thick material made of carbon atoms arranged in a honeycomb pattern, and it has some truly remarkable properties. The first is its high electrical conductivity. Graphene has very high electron mobility, making it an excellent conductor of electricity, which is advantageous for high-speed electronic devices and transistors. Second, it has exceptional mechanical strength. Graphene is 200 times stronger than steel, and its combination of strength and flexibility makes it ideal for creating durable electronic devices. Third, it's thin and transparent. Graphene is only one atom thick and transparent, making it useful for transparent electronics and displays. Lastly, it has high thermal conductivity. Graphene effectively dissipates heat, which is crucial for managing the heat generated by electronic devices. Thanks to these properties, graphene has various potential applications, including high-speed transistors, transparent electronics, and robust composite materials. Next, let's talk about carbon nanotubes. Carbon nanotubes are cylindrical structures made of carbon atoms, and they also have some impressive characteristics. The first characteristic is high electrical conductivity. Carbon nanotubes can be either metallic or semiconducting, and both types are excellent conductors of electricity. Second, they have exceptional mechanical strength. Carbon nanotubes have high tensile strength, making them suitable for lightweight structures. Third, they have high thermal conductivity. This makes them effective at dissipating the heat generated by electronic devices. Lastly, they exhibit chemical stability. Carbon nanotubes are chemically stable enough to maintain performance in various environments. Carbon nanotubes have a wide range of potential applications, from electronic devices to reinforced composite materials and medical applications, such as high-performance transistors, nanoscale electronics, and drug delivery systems. Now let's discuss the limitations of silicon. Silicon is currently the primary material used in most semiconductor devices, but it has some drawbacks. The first limitation is its electrical properties. Silicon's electron mobility is limited, which imposes speed limits on high-performance electronic devices. Second, there are physical limitations. As silicon transistors shrink to the nanometer scale, they encounter physical limits such as quantum effects. Lastly, there's the issue of heat dissipation. It's challenging to effectively dissipate the heat generated when integrating high-density transistors. This is why new semiconductor materials like graphene and carbon nanotubes are gaining attention. These materials have the potential to overcome silicon's limitations and play a crucial role in developing smaller, faster, and more efficient electronic devices. Research into these innovative materials is brightening the future of the semiconductor industry and will be a critical breakthrough in surpassing the limits set by Moore's law. 3D integrated circuits are also a good alternative. 3D integrated circuits differ from traditional 2D planar chip designs by stacking chips vertically. This is a crucial technological innovation for improving density, performance, and power efficiency in the semiconductor industry. 3D integrated circuits are vertically stacked, with multiple layers of semiconductor wafers or dies stacked vertically to form a single chip. Each layer can perform different functions and is connected vertically to transmit data and power. A technology called integrated interconnects is used, employing TSV through silicon via a small conductive pillar that penetrates the silicon wafer, electrically connecting the upper and lower layers. I think you can already see some of the advantages of 3D integrated circuits. First, there's the advantage of high-density integration. Since multiple layers are stacked vertically, more transistors can be integrated into the same area. This helps increase performance while reducing chip size. Additionally, shorter signal paths lead to faster transmission speeds. The shorter communication distance between layers reduces signal latency and increases data transmission speeds, which is highly beneficial for high-performance computing. Increased power efficiency is another big advantage. Shorter interlayer communication reduces the power required for signal transmission. Additionally, each layer can be optimized to reduce power consumption. It's also easier to integrate multiple functions. Different layers can be used to perform different functions, allowing for more efficient partitioning and integration of functions. For example, memory and processors can be placed on separate layers, enabling the creation of CPUs with much more functionality. But with every advantage comes a disadvantage, and 3D integrated circuits have their drawbacks. First, there's the challenge of heat management. With circuits stacked vertically, it's harder to dissipate heat, especially in the lower layers. Poor heat management can lead to performance degradation or failure. The complexity of the manufacturing process is another drawback. The manufacturing process for 3D integrated circuits is highly complex and precise. Of course, most new technologies face challenges in the manufacturing process. This is because it's difficult for new technologies to establish standardized processes. Ensuring the accuracy and reliability of TSV technology is a priority. Once reliability is secured, facilities for mass production will emerge, improving the situation. The substantial R&D costs before mass production can't be ignored either. Significant costs are expected until a stabilized structure is developed and standardized. However, if 3D integrated circuits become stable and reliable with established standards, the costs incurred up to that point will be fully recouped due to the immense economic scale of the application areas. First, they can be applied to high-performance processors. 3D integration technology can be used to design high-performance CPUs and GPUs, which play a crucial role in data centers and supercomputers. Considering that current supercomputers use a structure with a large number of processors connected in parallel, it could become possible to elevate PCs to the level of supercomputers. 3D integration technology will also shine in mobile devices like smartphones and tablets, where power efficiency is important. This technology can enhance performance while simultaneously improving power efficiency. It will revolutionize memory technology. 3D NAND flash memory uses 3D integration technology to vertically stack memory cells, significantly increasing storage capacity. It can also be applied in numerous fields that require many functions in small spaces. When combined with the new materials technology discussed earlier, it may be possible to develop chipsets capable of supercomputer-level computations while addressing heat issues. Beyond this, optical computing and photonic computing could be the ultimate solutions. We'll explore these topics next time. See you in the next session.
The first rule of channel is subscribe channel. Second rule of channel is click like. This channel will make you smart.